Good morning and welcome to this postgraduate course on advanced hydrology. We have been looking at the modeling of surface water. In the last class, we studied the rainfall runoff process and how we can model it. In this chapter, we have seen how we can do the modeling of infiltration process initially. So, given the infiltration equation, the rainfall data, we know how to calculate the effective rainfall heatograph. And once we have the effective rainfall, the next thing is to calculate what will be the DRH or what will be the runoff response. In the last class, we looked at the modeling of the surface flow process, and in which we said that the surface flow is composed of two components. One is the overland flow and other one is the channel flow. For the overland flow component, we derived a general expression for the flow depth, all right, from which we can also calculate the velocity of flow. So, the objective was to find out the flow depth and velocity, and we found a general expression. We could find out the flow depth when the overland flow is laminar as well as turbulent, all right. Initially when the velocities are small, we can use the laminar flow equations, and then later on we can switch to the turbulent flow equations. Similarly, for the channel flow, we looked at or we applied the Manning's equation in the channel, all right, Newton-Raphson iterative method, all right. This is what we had done in the last class. What we would like to do today is we would look at the modeling of the rainfall runoff process when it is unsteady. Okay. So, whatever we have done is for the steady state conditions. So, you find out what is the flow depth, what is the velocity when the steady state conditions have been reached. However, what happens or when the rainfall pattern is unsteady in itself, okay, then those models will not be applicable. So, what we want to do today is we look at one method, all right. Later on in later chapters we would look at some other methods, but we would look at a concept of what is called the time area diagram. Then we would look at an example on that, and then we would look at certain geomorphological parameters which are useful in understanding the behavior of a catchment with respect to the rainfall. Okay. How the response of the catchment in terms of the runoff would be there. We can get lot of inferences using the geomorphological parameters. So, we would get started today by looking at the concept of what is called travel time. Okay. What do we mean by travel time is that when the rain falls on the catchment, all right, it goes through lots of processes, all right. Now, we are looking at the rainfall runoff process on the surface flow. So, it will take some time, all right, to appear at the outlet. Let us say you have an effective rainfall impulse occurring in the upstream reaches of a catchment. How long it is going to take, all right, or the water particle to reach the outlet from different portions of the catchment, all right. This is called the concept of travel time. So, when we are talking of the unsteady flow modeling, all right, or we are trying to calculate the direct runoff hydrograph, we need to be able to find out how the input in a system is going to get translated in time, all right. If for example, let us say there is a rainfall 2 hours ago, all right, what will be the impact of the rainfall 2 hours ago on the flow or the runoff 2 hours later. Okay. So, these are the kind of things which we can do using this travel time concept. Okay. So, let me first define it as far as the travel time definition is concerned. Okay. The travel time of flow from one point on a catchment to another. Okay. And when we are saying another, it is normally the outlet we are looking at, okay, but not necessarily, all right. It could be between any 2 points also, can be deduced from the following equation. That is T, all right, is equal to summation of your delta Li over Vi, where I is an index that goes from 1 to, let us say, capital I, all right, where what is Vi? Well, Vi is the incremental velocity Vi is the incremental velocity for length delta Li, okay, and I is an index from 1 to I, that is capital I, for total length or total number of, representing the total number of increments. Okay. So, what we are saying here is basically that there is the travel time of water from any point in a catchment to the another point or to an outlet will be different, all right. We can calculate, that is, we can divide the path of water of travel of water from one point to the other into different segments of length delta Li. Once we have done that, we can estimate the average flow velocity in that component, all right. Once we have the lengths, all right, and the velocities or the average velocities, we can find out the travel time between those two segments, all right, and then we can sum all those up. So, we can find out the total time for water to travel from one point to the other. Okay. So, this is a very simple concept. Normally, when we are dealing with real catchments, there are two major components. One is the overland flow, other is the channel flow, in which the average velocities would be quite different or significantly different. Okay. Within the overland flow, we can divide the catchment into further delta Li's, maybe 100 feet each or whatever. Okay. So, this is the concept through which we can try to estimate the travel time. Now, related to the travel time, I am sure you all know what is called the time of concentration. Okay. This is another important term which is called time of concentration. What is time of concentration? Well, it is nothing but the time of travel for a drop of water, or for water we are saying, to travel from the remotest location to the outlet. Okay. It is very simple. In the simple terms, that is how we define what is called the time of concentration. Outlet of the catchment. Okay. So, if you want to look at this concept, all right, let us say this is your catchment in which there is a major channel, all right. Now, there may be a point on the boundary, all right, which is the remotest location, all right. So, the time for water to travel from this location, and let us say this is your outlet, that is where we want to measure or find out or estimate the direct runoff response. Okay. So, time taken by water to travel from the remotest location to the outlet is called the time of concentration, all right. What is time of travel? Well, we can find out the time of travel, all right, from here to here or from here to the outlet or any 2 points, all right. So, we can calculate the time of travel or estimate the time of travel that way also. Now, when we are doing the unsteady flow modeling or the rainfall runoff modeling, what we need to do is we need to find out what is called the concept of isochrone. We need to understand what is an isochrone. Using this time of concentration concept, which is the maximum travel time in a catchment from traveling from the remotest location to the outlet, we can develop what is called the isochrone, all right. As the name suggests, what is an isochrone? An isochrone is a line joining equal times of travel in a catchment. Okay. So, if you define it, isochrone is defined as a line joining equal times of travel in a catchment. All right. When we are talking about the time of travel, obviously, if we are not saying anything, it is with respect to the outlet. All right. So, we are trying to find out the time of travel to the outlet. Okay. So, if you look at this catchment which we have drawn here, all right, let us say this is your outlet. Okay. We want to draw a line, okay, from where the time of travel is same. All right. So, let us say we are looking at this line. All right. So, any drop of water that falls on this line or close to this line will take, let us say, 1 hour to reach the outlet. Okay. So, we say that this is a line or this is an isochrone corresponding to 1 hour, all right, or some interval delta t. Okay. Similarly, we can draw another one which is further upstream in the catchment, and that will be 2 hours, all right, 3 hours, 4 hours and so on, and then final will be your time of concentration. So, all these lines which we are seeing, all right, these are actually called isochrones. The concept of these isochrones is extremely important. Why? Because the area between these two lines or this inter-isochronal area is an important concept. Why? Because what we do is we assume that this whole area, okay, this takes about 1 hour to reach the outlet or whatever the time delta t is. The next one, A2, we say is going to take 2 hours or twice of delta t, all right, and so on. So, with that you see that whatever input that is falling on the catchment, we would be able to translate that input in time, all right, so that we will be able to find out the direct runoff hydrograph response, how the shape of the hydrograph would be. Okay. So, let us move on and then first look at the concept or how we can actually calculate the direct runoff hydrograph from what is called a time area diagram. Okay. What is a time area diagram? All right. We just looked at the concept of travel time, time of concentration, isochrones and inter-isochronal areas. All right. All these things are very important or useful in developing what is called a time area diagram in a catchment, okay, which can be used for calculating the DRH response. All right. So, let us first look at what is the time area diagram. TAD, or it is also known as time area curve. Let me say time area curve. Different book would follow different terminology. So, let us not get confused about that. So, either the time area diagram or the time area curve is a diagram, all right. We could be looking at it graphically or in a tabular form or curve which gives inter isochronal areas versus travel time. Okay. So, it is nothing but a curve or in the tabular form, it is the data of travel time with respect to or versus your inter-isochronal area. All right. So, what it will be able to give is that much of area in the catchment or that fraction, all right, water takes about 1 hour to travel. That much or A2 will take 2 hours and 3 hours and so on. Okay. So, we can define area versus time curve, which is the time area diagram. Okay. All right. So, let us say that we have this catchment in which this is your stream network. Let us say that we have divided this into using the isochrone into different isochronal areas. Let us say this is A1, A2, A3 and so on, AI. Alright. Well, I am sorry, the AI has to be the last one, that is capital I, and this is let us say A small I. Okay. Alright. So, say let your A1, A2, A3 etc. all the way up to A capital I. Alright. Subscript is going from small I is going from 1 to capital I, be the inter isochronal areas. All right. So, let me first do that here. What is a time area diagram or your time area curve, which is nothing but your travel time here and inter isochronal areas. Okay, is here. It can be in square meters or square kilometers or hectares, whatever. So, let us say it is 0, it will be 0, then you have T1, it will be A1, T2, A2 and so on. You have T capital I up to A capital I. All right. So, this is called your time area diagram, this table, or you can plot it, that curve. Okay. And that is what we have defined here. Okay. This is your inter isochronal areas, okay, while we are doing the modeling for the direct runoff hydrograph. Also, let the R1, R2 and R3 etc. all the way up to R subscript capital M be the effective rainfalls. All right, that is falling on the catchment. All right, let us say that it looks like this. These are the ERH. Okay, this is your ERH. So, what are these things? This is your R1. Well, this different impulses are, let me write it here, R1, this is your R3, this is your R2, all the way up to the last one is your R capital M. Okay. And let us say your Q1, Q2 all the way up to Q capital N, all right, be the DRH or the direct runoff hydrograph ordinates. Okay. So, what we are saying is that the total number of ordinates in your time area diagram are how much? This is I. The total number of ordinates in your ERH is how many? This is capital M. All these numbers are important and they would be different. Okay? They do not have to be same. And then the total number of ordinates in your direct runoff hydrograph is, let us say, capital N. Okay? We would look at a relationship between all these later in the course, but for right now let us say these are your maximum number of ordinates in different physical parameters. Let us say that this is an index I, all right. This is represented by some index small m and this is represented by an index n. Okay. So, we are defining the lower case letters as the index and the upper case letters is the maximum number of ordinates. Okay. Then the DRH ordinate, all right, will be what? Q subscript n, where n will go from where to where? 1, 2 all the way to capital N, right, is given by using this time area concept the discrete convolution equation. All right. This discrete convolution equation is something which we have not seen yet. All right. But what we will do is we will just look at it in the discrete form and we will derive this equation in the continuous form in the next chapter. All right. So, what I will do is I will just give you this equation and explain each and every term in it and how we actually use this discrete convolution equation to calculate the output from it, all right, in terms of DRH response. Okay. So, how does it look like? Okay. This looks like this. It will give you the ordinate q n as summation running from I is equal to 1 to small n as long as it is less than or equal to capital M. And this term in the summation is R I times A small n minus I plus 1. Okay. So, this is a very important equation which can convolute your input into output, or it can translate your input in time and give you the response at the outlet in the form of DRH. Okay. This is your discrete convolution equation. Okay, which translates the input response or input into output through time. All right. Okay. So, let us look at the application of this equation for any data. All right. Let us say you have capital M is equal to 2, 4, 5, 6. All right. There may be 2, 4 or 5, 6 impulses in your effective rainfall histograph. You may have a catchment in which you have done the time area diagram. How do we actually calculate this time area diagram? We take the topographic map, all right, we estimate the approximate the travel times, and then we draw the isochrones using our knowledge of contouring, and we can have any delta t, all right, any desirable contour interval, and then let us say we have the capital I or A1, A2, A3 up to capital I. Then q is something which we want to find out, which is the DRH ordinate. Okay. So, using this equation, how can we do that? Let us say you want to use this equation for n is equal to 1. Okay. Now, before I actually go to that, let me first explain what is this concept I going from 1 to n less than equal to capital M. This is important. Okay. What we mean by that is the summation, this summation will run from 1 to small n. What is small n? Small n is the index of DRH ordinate, all right. It is not capital N, all right. Small n will keep on changing from 1, 2, 3, 4, it will go all the way up to capital N, but small n is the index, all right. For example, you want to find out what will be the DRH ordinate at the end of first hour. For that, n is equal to 1, all right. If you want to find out the DRH ordinate at, let us say, some nth ordinate or nth time step, all right, or fourth time step. So, that value you have to take accordingly. Okay. Now, the summation will run from 1 to n as long as n is less than or equal to capital M. Okay. This small n should not be more than capital M. What is capital M? Capital M is the total number of effective rainfall impulses in the ERH. Okay. So, this small n should be less than or equal to that value of maximum number of impulses in ERH. All right. That is to say, if in opening up this expression or this summation, when you encounter n values which are more than capital M, they will just vanish. all right. So, they will not be existent, or you just put them equal to 0, all right. This will become clear when we take some example later on. Okay. So, let us say that what will be your q1 for n is equal to 1. If you utilize this equation, just think about it, what will be q1. If you look at the summation, this summation will run from where to where? Now, we have said that small n is equal to 1. So, the summation will go from 1 to small n, which is 1. So, there will be only one term in the summation. Okay. So, you have r, I is going from 1 to 1. So, this is 1 multiplied by a, area. Which area? Well, small n is 1 minus I is 1 plus 1. Is it clear? So, this will be nothing but R1 A1. Is it clear? So, let me draw a diagram here quickly. So, this is your, let us say these are your areas. This is A1, this is A2, this is A3, this is A4, this is A5 and so on. Okay. Now, what this equation is telling us? Physically, if you want to think about it, what this equation is telling us physically? It is saying q1 or the direct runoff hydrograph at the end of first hour. Let us say 1 hour is the delta t, for example, for demonstration. So, the DRH at the end of first hour is what? Is nothing but R1 multiplied by A1. That is the contribution from the catchment during the first hour. What is A1? A1 is the entire isochronal area corresponding to 1 hour, all right. So, there will be no response at the outlet at the end of first hour from A2, A3, A4 and so on. Why? Because the travel time concept we are using, at the end of first hour only A1 is contributing. Okay. So, that if you come here, the q1, the contribution is coming from A1 only. So, if you look at this diagram, all right, the runoff response here, you see that the response at the end of first hour will be only from A1, all right. That is what this equation is telling us. Now, look at, let us say n is equal to 2. At the end of second hour or at the end of second time interval, what will happen? The contribution will come from where? Obviously, the contribution will come from both areas A1 and A2, but which rainfall would be used? Okay. If think about it, and then we will use this equation, and then we will try to deduce what is actually happening and which area is contributing at what time. Okay. All right. So, small n is equal to 2 in that equation, this equation that is. So, you are saying q at the end of second hour will be equal to what? How many expressions or how many terms will be there in the summation? Small I varying from 1 to small n, and the value of small n is what? 2. So, there will be 2 terms. Okay. So, I will run from 1 and 2. So, first we will write the expression for I is equal to 1. What would that be? Well, it will be I1, all right, I is equal to 1 times A, small n is what? 2 minus 1 plus 1, all right. Just simply apply this equation like a computer program. Okay. Plus there will be another term. So, you have R, now I is 2, all right, times area, which one? N is constant, N is 2 here. Okay. So, we have not changed n. So, this is 2 minus 2, all right, I is 2 plus 1. Okay. So, I is 1 here and 2 here, but n is constant, n is constant, all right. Okay. So, that means your q2 would be equal to what? It will be R1 A2 plus R2 A1. Does that make sense? Okay. Now, think about it with respect to this diagram here. What this equation is telling us is that the runoff response at the end of second hour, this one q2 is equal to what? Is equal to the contribution from area A2. Which contribution? The rainfall which fell during the first hour. okay, the rainfall that fell on the whole catchment during the first hour, all right, on A2 will appear at the outlet at the end of second hour. Similarly, the rainfall R2, that is the rainfall that fell during the second hour, all right, that will contribute from A1 at the end of second hour. So, you see that this A1 rainfall R2 will appear here. Similarly, A2, the rainfall that fell during the first hour will appear at the end of second hour. So, you can try to think about it and try to make sense that intuitively this equation is making sense, which rainfall impulse will appear at the outlet at what time. This pure translation or this translation in time is taken care of by this time area diagram. So, it is a very important tool. Physically it is important to understand the mechanism, otherwise mathematics is very simple. Okay. All right, let us look at one or two more cases. Let us say you have n is equal to 3. All right. What will be the answer? Now, you see a pattern. Now, your Q3 will be equal to, I am going to write it directly, you would have R1 A3, okay, plus R2 A2 plus R3 A1. Okay. What is this equation telling? You can apply the same logic. The runoff at the end of third hour is contributed from all the three areas A1, A2, A3, right. But which rainfall is effective on A1 at the end of third hour? It is the rainfall which falls at the during the third hour. Similarly, the rainfall which falls on A2 during the second hour, all right, will appear at the end of third hour here. Similarly, A3 will be multiplied by R1 and so on. Okay. So, there is a pattern here. So, n is equal to 4 you can write directly, which would be Q4 is equal to R1 A4 plus it is going to be R2 A3 plus R3 A2 plus R4 A1 and so on. So, you can successively keep on applying this equation, which is called the discrete form of continuity equation. So, you can find out the direct runoff hydrograph, all right, and it would look like this. So, you have the different times and then you have q, and these are the different ordinates you have calculated q1, q2, q3 and so on. So, you see that the computation of the direct runoff hydrograph using the time area diagram, it is a very simple process, okay, using this discrete convolution equation, all right. However, whenever we have the rain falling on the catchment, it is getting converted into runoff. What is actually going on in the catchment is that the water is going through two hypothetical processes, all right. We would write these down and then look at the limitation of this time area diagram method, all right. So, in your rainfall runoff process or the physical process, the input, which is your water, goes through two main processes, let us say. What are those? Well, it is, one is the translation in time. What happens to the effective rainfall? It gets translated in time, okay, and also it gets attenuated, or you have attenuation due to storage. Okay. So, in the rainfall runoff process, you have these two components which we need to model in any mathematical model, all right. This time area diagram, the method which we just looked at, accounts for only translation in time. It does not account for the attenuation due to storage in the catchment, all right. So, if you write the limitation of the time area diagram is what? That it accounts only for pure translation, or translation I should say. it does only pure translation. Can you tell me any method, rainfall runoff method, that is converting effective rainfall into direct runoff hydrograph, which accounts for both translation in time as well as attenuation effects in the catchment storages? It is unit hydrograph. Okay. I am sure you all have seen this. So, you can say that UH accounts for both translation and attenuation effects in a catchment. Okay. Attenuation effects in a catchment. Therefore, it is more accurate than time area diagram. Obviously, any mathematical model which is able to account for all the processes through which the input is going through would be more accurate. All right, we will come to the unit hydrograph in the next chapter. Okay. What I would like to do next is look at an example of the time area diagram. Okay, how we can actually develop it and how we can use it. So, next thing we are going to look at is example on the time area diagram. Okay. In this example, I am going to first write it down and then we will see how we can solve it. A rectangular paved area of 150 meters by 450 meters, okay, has a longitudinal drain along one of its longer edges. Okay. The time of concentration in this rectangular paved area or the catchment is 30 minutes. Okay. The maximum travel time is 30 minutes and consists of this total 30 minutes consists of 25 minutes for overland flow. As I said, it takes more time in for water to travel as overland flow and less time during in the channel, right. So, it takes 25 minutes for the overland flow across this pavement. Okay, to the drain or towards the drain along the longitudinal edge, and 5 minutes from the upstream end of the drain to the outlet. Okay. So, total of 30 minutes, 25 minutes in overland flow and 5 minutes in the channel flow, okay, or along the drain. Okay, what you have to do is A, construct the isochrones at 5-minute interval. Okay, so we are looking at this example. A part we have to construct the isochrones at 5-minute interval, and B, in the second part we have to develop what is called your time area diagram. Okay. All right. So, what we will do is let us look at this problem first graphically or arrange all this data so that we can understand the problem. Okay. The length of the pavement is 450 meters, that is given to us. all right, and this way, or the width is how much? It is 150 meters. Okay. So, it is a parking lot or something. Okay. There is a drain along the longitudinal edge. Let us say this is the drain. Okay. So, the water actually travels from right to left. All right. Let me just draw this, okay, like this. All right. So, this is the overland flow, all right, and then it comes into this drain and then it goes down like this. All right. That is the flow pattern, okay, we are looking at. Now, what we have to do is we have to draw the isochrones on this. All right. What are the isochrones? Isochrones are the lines joining equal times of travel. Okay. So, what we can do is whenever we have to do contouring, what do you do on a map? You put the benchmarks, all right, or you put certain spot elevations. So, what we will do here, try to do here, or in any kind of problem which is similar to this, at important points or at some points on this graph, you put the travel times which are available to you, okay, and the information that is available to me is that the maximum time of travel is 30 minutes, all right, and the maximum time of travel in the drain is 5 minutes. Okay. All right. So, if you put that information, this is the remotest point, right. So, from here it is 30 minutes. All right. What about this point here? From here, how long does it take for and by the way, this is your outlet. So, the water is taking 30 minutes from here, all right. How? 25 minutes along the overland flow and 5 minutes along the drain. Similarly, from here it is taking 25 minutes as the overland flow and then it reaches the outlet. What about this point? Just at the upstream end of the drain, this takes 5 minutes, all right. This edge is the outlet itself, so it takes 0, all right. So, now we have these 4 points, all right, on this rectangle at which we have marked the travel times. Okay. How can we find out or how can we draw the isochrones at 5-minute interval? Well, we can do linear interpolation, all right. So, if you use the linear interpolation concept, then let us say we can divide it into 1, 2, 3, 4, 5 parts. 1, 2, 3, 5 parts, this one and 1, 2, 3, 4, 5 parts, all right. Now, what will be the time of travel from here? Okay. So, it is 5 to 30, all right, along this width, and you have divided this into 5 parts, all right. So, it has to be then 25 from here, it is 20, 15, 10 and this is 5, right. Similarly, this will be 5, 10, 15, 20 and 25. Okay. So, what we have done is we have found out the points, all right, of times of travel. Now, what are the isochrones, which is the part A in this problem? We have to find out the or develop the isochrones, all right. Isochrones are the lines joining equal times of travel. So, now you have 2 points in the catchment which have equal travel times. You have 25 here and you have 25 here, you have 20 here and 20 here, all right. So, all you need to do is just join these points. Okay. So, let me try and do that. You can join 25 with 25, 20 with 20, all right, 15 with 15, 10 with 10 and this is the 5, 5 with 5. So, these are your isochrones, all right. You can subdivide all these areas. Let us say this is your A1, this is A2, this is A3, A4, A5 and A6, all right. So, part A is the isochrones, all right, by dashed red lines. Okay. Now, part B we have to develop the time area diagram. What is time area diagram? It is time versus these A's, interisochronal areas. Now, how do we find this A1, A2, A3, A4, A5, A6? Well, we have the width and the length of the catchment or this paved areas. We have divided that into 5 different parts. So, each of them will be 30 meters each. All right. So, what will be your A1? This area A1. A1 is a triangle. All right. If you see, its one width is 5 meters, the other way it is 400 and not 5 meters. This is 30 meters, and the other way it is 450 meters. So, area of a triangle is half of base into height. Half of base is, let us say, 450 meters multiplied by how much is this? All right, this is, let me try to do it here. You have divided it into 1, 2, 3, 4, 5. Total was 150. So, each of it would be how much? 30. You see that? So, each strip is 30 meters. All right. So, this is 30 meters. Okay. This would be equal to 6750 square meters. What will be A6? This area will also be equal to A6. You see that this A1 and this area A6 are same. All right. Why? Because you have same base and same height. Okay. All right. So, A1 is equal to A6. Now, similarly, you have A2 is equal to A3 is equal to A4 is equal to A5. All right, which are parallelograms of equal size, all of them. Okay. That will be equal to what? Using this geometry, you can see twice of, let us say, A1. All right. One is a triangle, other is consisting of twice of that triangle. All right. So, it will be twice of your 6750 square meters. So, which would be 13,500 square meters. All right. So, your time area diagram then is given as follows. All right, which is your time is in minutes, I should say, 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, and the maximum is 25 to 30. Okay. These are the intervals, and then your interisochronal areas in square meters is how much? Well, it is for first 5 minutes, which is A1, is 6750, that is A1. Then other one, all of the middle areas are equal, which is 13,500 square meters. This is 13,500, 13,500. This is also 13,500, and the last one is equal to the first one, which is 6750. All right. So, let me write it. This is A2, A3, A4 and A5, and the last one is A6. Okay. So, this is your answer B. So, you see that we have taken a very simple example of taking a catchment, knowing the time of concentration, we can do put some certain spot elevations in terms of travel times, and then do the contouring. This contouring of isochrones can be done either manually on a map, or there are sophisticated software available these days which can do that. All right. Once we have done that, we can measure the interisochronal areas on the map on a natural topography, or if you have a simple example like this, we can use our manual calculations. All right. Now, I would like to extend this particular example, and I will give you a homework type of problem in which you solve part C, okay, to calculate the DRH from the time area diagram which we have developed, okay, using the following ERHs. Okay. First one is very simple. Let us say it is 2 centimeter. All right. This is your effective rainfall, and this is your time. All right. And this time I am going to say is time interval is 5 minutes. So, let me say that for this ERH delta t is 5 minutes, so that there is no problem. Okay. So, that is part 1, and the other one, let us say this is 1 centimeter, this is 2 centimeters, and this is 1.5 centimeter. Okay. So, what you do is you try to solve this problem, all right, in which there are 2 effective rainfall heatographs are given to you. Okay. So, after having looked at this example, what we would like to do, the last thing in this chapter is about certain geomorphological parameters. Okay. So, what we will do is we will look at if we do not have a lot of information about rainfall or the gauges in the catchment in terms of flow, then what we can do is we can take the topographic map of the catchment and then develop certain parameters or characteristics. All right, we can calculate certain parameters using those topographic maps and try to infer certain information about the runoff response of the catchment when it is subjected to rainfall. Okay. So, we look at few of these geomorphological parameters. All right. First one of them is what is called the Horton's stream ordering system. All right. You may have a large catchment in which there may be a main channel, all right, or the downstream channels. They would be upstream channels, all right, small channels which will be forming very small channels in the upstream catchments. All right. So, what Horton has done is he has developed a certain notation or system of numbering or ordering those streams, okay, so that we can calculate many physical or these geomorphological parameters for each of these different types of streams. Okay. So, what they have said is that the small or the smallest recognizable channel in the catchment is given order 1 or the first order. Okay. And then the other rule is when 2 channels of order I join, the channel of order I plus 1 is formed. Okay. So, we will try to look at this concept in a graphical manner. Okay. Let us say this is the catchment we have, in which there is a main channel, there is some tributaries to that, there is some further sub tributaries, other small streams joining, all right. Then there may be other streams joining them, all right. Similarly, other places like this. Okay. So, this is your network of streams. All right. So, upstream you have very small channels, and then as you go downstream you will have the bigger channels. All right. So, how do we order it? Using the Horton's stream ordering number. Well, the smallest recognizable channel is 1. Okay. So, let me use a different color actually. Let us say this is 1, this is also 1. These two will join, they will form 2. All right. And then this is the smallest one. So, this is 1, 1 and 2 will join, will form what? It will remain 2. Okay. When 2 and 2 will join, when the 2 streams of order I or 2 will join, then I plus 1 will be formed. All right. Otherwise not. Okay. So, this is 2, and let us say this was also 2. All right. And then 2 plus 2 will be 3. Okay. And let us say this is 2. All right. So, this 3 and 2 will be 3 here, and let me order this one here. So, this is 1, 1 and 1 join, this is 2, this is 1. So, this is 2, this is 1, this is 2, this is 1, and this is 2. Okay. And then 2 and 3 would join, it will form number 3. All right. So, this way you see that we can keep on ordering these different channels or numbering these channels using the Horton's concept. All right. And then the maximum order in the example which we have drawn is what? It is 3. Okay. And let us say in general it is capital I. All right. So, your order index is I, it will vary from 1 to capital I. All right. So, this is the ordering system as per Horton. Okay. The next parameter we are going to look at is what is called the bifurcation ratio. It will be denoted as RB, bifurcation ratio, and this RB is nothing but Ni over Ni plus 1, and people have found out that this is a constant and it ranges between 3.0 to 5.0. But let me first define what is Ni. As it suggests, it is the number of channels, it is the number of channels of what? Of order I, okay, which we have just defined above in the catchment, in a catchment. All right. So, you see that higher the RB, what is the RB? It is the bifurcation ratio. Higher the RB means what? It would mean that there is higher number of what? Of upstream channels. Okay. So, there are more channels, okay, in the upstream reaches. What would that mean in terms of the drainage capacity? If you have more number of channels, the catchment will be able to drain water very quickly and efficiently, right. So, higher the RB, you will have good drainage capacity of your catchment. So, you see that by looking at the this bifurcation ratio RB, we would be able to say something about the hydraulic efficiency of a catchment, or we can compare the two catchments. Okay. Moving on, the next ratio or the next parameter we would look at is called the length ratio RL. It is defined as the ratio of Li plus 1 over Li. Okay. It is also called law of stream lengths. All right, where Li is the average length, Li is the average length of stream of order I. Okay. Similarly, we can argue that higher the Li would mean what? Mean the length of the downstream channels is higher. Okay. That would also mean you would have good drainage capacity of the catchment. The next parameter is the area ratio, which we would define as RA, and RA is given as AI plus 1 over AI. Okay. And what is AI? Well, it is the average area of catchment drained by stream of order I. Okay. When you compare the two catchments, one with higher RA or the area ratio, that would mean what? That would mean greater area drained by what? The downstream channels, okay, as compared to the earlier one. All right. So, that is also indicative of good drainage capacity of the channel or the catchment. Okay. All right. Moving on, the next thing we are going to look at is what is called the drainage density. As you can see, we can estimate or calculate all of these geomorphological parameters using the topographic map. This D is defined as summation of L I j, and I need two summations. One is I running from 1 to capital I, all right, all the streams, and then j running from 1 to n I, okay, and this whole thing divided by A I, all right, where L I j is what? Is the length of jth stream of order I. So, you see that this drainage density is what? It basically represents the ratio of the total length of streams divided by the total area. All right. So, it is the length of the all the channels, all the streams per unit area of the catchment. All right. So, this is called the drainage density. All right. Obviously, when you compare two catchments and we can calculate their drainage densities. So, let us say you have two catchments, one has lower drainage density as compared to the other. All right. Which one will be more hydraulically efficient? Obviously, the one with higher drainage density. Why? Because the one with the higher drainage density has higher length of the total number of channels, all right, or greater length. So, you can say that higher drainage density means what? Greater hydraulic efficiency or drainage capacity of the catchment. Okay. The last one in this we are going to look at is called the length of the overland flow. Okay. This is denoted by LO, and people have found out that this LO is nothing but 1 over 2D, all right, which is the average length of your overland flow. Okay. So, you see that we have defined a lot of these parameters, the bifurcation ratio, the area ratio, the length ratio, the drainage density, and so on. Okay. With that, I am afraid we come to the end of this chapter, which is on the surface water. Okay. So, we have looked at the modeling of the surface water in this chapter in a comprehensive manner. All right. The next chapter is on the unit hydrograph. all right, which is a more comprehensive or little bit more detailed modeling of the rainfall runoff process, in which we would look at various types of functions which are needed to develop this unit hydrograph concept. Okay. So, I would like to stop at this point of time, and then we will start the next chapter in the next class tomorrow. Thank you.